Hi everyone, welcome to Project Group 5 presentation. Today we'll be talking about the study of virtualization technologies and security implications. First of all, the objectives will start with introduction, the literature review, the security challenges, best practices, and recommendations. The roots of virtualization technology can be traced to the 1960s, originally conceived to enable multiple user access to mainframe computers. It wasn't until the late 1990s that virtualization became widely available to the public. With the advent of products like Virtual PC and VMware, transitioning from its mainframe-centric origins to the broader x86 architecture, making it commercially accessible. The introduction of commercial virtualization solutions for x86 systems marked a fundamental moment, enabling businesses to create and manage multiple virtual environments on a single physical hardware setup. This was crucial for the development and expansion of data centers and enterprise computing, providing the foundation for system management and disaster recovery improvements. The growth of cloud computing in the early 2000s was significantly propelled by advancements in virtualization technology. Cloud services such as AWS, Google Cloud Platform, and Microsoft Azure rely on virtualization to offer scalable and on-demand resource provisioning. Virtualization plays a vital role in modern computing, particularly in enabling and optimizing cloud services like infrastructure as a service. It allows for the abstraction of physical hardware into multiple virtual environments, leading to efficient resource utilization, reduced costs, and enhanced flexibility in managing computing resources. The continuous growth and innovation in virtualization have been crucial in driving the expansion of the cloud computing market, making it an indispensable tool in the development and deployment of modern IT infrastructure and services. Virtual machine monitor architectures are fundamental to the functioning of virtualization technology. There are two main types of VMMs. The type 1, also known as bare metal hypervisors, run directly on the host hardware to control the hardware and manage guest operating systems. Examples include VMware, Microsoft Hyper-V, and Xen. They offer high performance and efficiency because they interact directly with the physical hardware without an underlying operating system, making them ideal for enterprise environments. The Type 2 VMMs or hosted hypervisors run on top of an existing operating system. This means that the VMM is essentially a software layer installed on an operating system such as Windows, Linux, or Mac OS. They are often used for development, testing, and educational purposes, where full isolation and performance are not as critical, and the ease of use and flexibility are preferred. Virtual machine monitors or hypervisors play a crucial role in virtualization, providing a variety of functions to manage and maintain virtual environments efficiently. One of the core functions of the VMM is to provide isolation between different virtual machines running on the same physical machine. This isolation ensures that processes in one VM cannot interfere with the processes in another VM, maintaining data confidentiality and system integrity. VMMs emulate hardware devices for virtual machines, allowing each virtual machine to operate as if it has its own set of hardware resources. This emulation is crucial for the VMs to perform tasks independently of each other, even though they share the same physical hardware. VMMs manage the execution of privileged operations for guest VMs. Certain operations that require elevated privileges, which are typically restricted to the host system, are managed by the VMM to ensure secure and efficient execution within the virtual machines. VMMs provide comprehensive tools and interfaces for managing virtual machines, including creation, execution, monitoring, and termination of virtual machines. Advanced management features also include dynamic resource allocation, load balancing, and live migration of virtual machines from one host to another without interrupting services. I'll be handing it over to Xinman to continue the presentation.
Virtualization technology has become a cornerstone of computing, providing a service platform that is both scalable and highly available. But as it's used more and more, we are starting to see new security challenges that require new technologies and strategies. The introduction of virtualization may invalidate some traditional security policies. For example, in a virtualized environment, multiple virtual machines share the same physical hardware resources, which breaks the assumption of physical isolation in traditional security policies. Therefore, discussing security challenges in virtualization is critical not only to increase our awareness of potential security issues, but also to promote the development of more effective safeguards to ensure the security and reliability of virtualized environments. There are two main types of security challenges. The first type is vulnerabilities in the virtual machine monitor, and the second one is resource sharing. A virtual machine monitor is a core component of virtualization technology that manages virtual machines and regulates the interaction between the host hardware and the virtual machines. One of the main responsibilities of the VMM is to ensure strict isolation, meaning that it needs to prevent applications running on one virtual machine from viewing or interfering with applications on another virtual machine, and prevent unauthorized access to the host system. However, if there's a vulnerability in the VMM, this isolation can be compromised and become inadequate. A breach of the isolation mechanism can lead to serious security risks. If these vulnerabilities cause the protective walls between virtual machines or between virtual machines and the host system to be weakened, an attacker could break into other virtual machines or even the entire virtual machine manager itself. This situation is called virtual machine escape, in which a program running in a virtual machine is able to break through the virtual layer set by the VMM and gain access to the host machine. This not only challenges the security foundation of virtualization, but also poses a significant threat to the security of the host machine and all its virtual machines. In a virtualized environment, multiple virtual machines or users share the same physical resources, such as memory, storage, and processors. This resource sharing can lead to various security issues, such as side channel attacks, data remnants, and also provides opportunities for man in the middle attacks. The threat of side channel attacks become more pronounced in a virtualized environment, mainly because virtual machines share key resources, such as processor caches. This sharing scenario provides malicious actors with an opportunity where they do not need to directly access sensitive data. Instead, they can infer private information by observing and analyzing the access patterns of nearby virtual machines to these shared resources. For instance, by monitoring which cache lines are frequently accessed, an attacker might deduce the operations being performed by other virtual machines, thereby indirectly obtaining sensitive information. Data remnants occur due to the sharing of storage and memory, where previously stored information might persist even after deletion. For example, a file that has been deleted by one user can still be accessed through shared storage by another user, posing a risk of unauthorized access to sensitive information. Regarding man in the middle attacks, if attackers are able to eavesdrop or inject malicious code into these shared resources, they have the opportunity to intercept and tamper with communication traffic, thus executing man in the middle attacks.
Thank you, Simon. So, as regards the best practices for preventing such security vulnerability, or to at least mitigate the risk, we have isolation enhancements. It is very crucial for us to make sure that the activities of one virtual machine is not affecting a separate virtual machine, whether the virtual machine decides to do it or not. This is very important so as to prevent adversaries from using a virtual machine to attack other virtual machines. It can also be seen as a prevention against system uh, contradicting themselves. A system's action could also be affecting a separate system's action. So it's very important to enhance isolation. It's one of the key things in securing our VMs. Also, some administrators see updates as a convenience. It's when they have the time to that they should update, and it should not be perceived this way. Updates are not just generated for being updates, they are generated because there are some existing vulnerabilities within the system that they would like to patch up. So updates should be seen as emergencies, things that should be considered immediately and planned for immediately rather than an afterthought. As regards data sanitization, there's going to be a lot of data being fed into our systems from the tenants, from the users, even from trusted stakeholders. But we always have to sanitize the data being received because we can't 100% guarantee any uh, anybody's trust. We have to treat everybody as a potential adversary. So it is quite important to make sure that any form of data being received by the system is properly sanitized before it's even passed into the storage or being processed. Secure communication channels. Sometimes it's understandable that we might want some VMs to be able to communicate with each other, and that is okay. But we always have to ensure that these systems are communicating through encrypted channels, or they have digital certificates to ensure their integrity. This is quite important because we want to prevent the man-in-the-middle attacks. We don't want anybody sniffing around our business, knowing exactly what is going on, even if they're able to access what it is. Then secure resource allocation and monitoring. It's very important to make sure that we secure uh, resource allocation. Definitely, firms are going to have different levels of trust, and we should always avoid connecting or allocating resources from trusted spaces to untrusted users. So this concept is enlightening because we don't want to just put all our users in the same brackets. There are going to be some users that are typically more trusted than others, and these users should not share the same memory location, the same resource allocation with users that are not trusted. We also have to ensure that we monitor how these resources are being used because a lot of the time when adversaries take control of our VMs, you'll be able to spot it from the pattern of how they use these resources. For further recommendations, we would recommend collaborative threat intelligence sharing. This could come in form of conferences, in form of papers, or in form of seminars. This is beautiful because there is no island of knowledge. I believe each and every system has their own peculiarities and their vulnerabilities, and it's always better when somebody experiences some form of exploits, others learn from it, rather than letting everybody experience the same level of exploits. So it's always important to collaborate on our threat intelligence and educate each other on potential vulnerabilities and mitigation strategies for it. The use of noise and obfuscation techniques cannot be overemphasized because in as much as we're trying to safeguard our resource allocations, some adversaries might be able to sneak to take advantage of our side channels that are not intended pathways for disclosing information. So most always have to disguise our communication or our operations in noise because, for example, timing attacks, they take note of how much time a certain process takes to dictate what kind of process it is. So by making the all processes take uniform time, although it would reduce productivity, but it's a very safe strategy in order to prevent adversaries from being able to assume or guess kind of operations that might be running. Security awareness and training can also not be overemphasized. For instance, when there are not users and tenants are most likely most open source of vulnerability. They have the most attacking surface. So it is good to educate them on potential vulnerabilities and the impact of these vulnerabilities on not just us, but also themselves. They fail to prevent it in their own capacity. Then we have to limit our connections, our resources, and our privileges on a need to have basis. We don't just assign memory spaces because we can. We restrict it to the functions that the VM is expected to perform, and then we make sure the privileges they have, the connections they make are because they need it, not because we can. So if a VM doesn't need to connect with another VM, then don't make it connect. Don't route the information through that VM just to get to another VM. It's not a safe mechanism. In conclusion, if we think about virtualization, we can liken it to yin and yang, which is the symbol of good and bad we mix together. Virtualization in its sense it shouldn't be something that we would go for if we're looking towards security, because the concept of having multiple systems within a system highly increases our level of vulnerability, because a lot of by accessing just that one system, you might be able to access so many other systems that are operating within it. But because of the benefits that we enjoy from it, we've decided that the risk is worth it. So it reflects entirely on what security is and what cybersecurity is. It's just knowing that we are willingly accepting some level of vulnerabilities, and then we are trying to balance it. So virtualization itself is virtualization and security extension is trying to balance both the security and efficiency of our systems, trying to secure it without necessarily restricting our users from being able to have a comfortable time using our systems. Key takeaways are that we should always remember that virtualized environments, despite their numerous advantages, also introduce specific vulnerabilities that might not otherwise exist. Also, the divide and conquer strategy helps us to simplify the complexity of securing virtualized environments and also the effectiveness of implementing it. So it helps us to find it easier to implement, and this also makes it more effective. It's also key to remember that no defense is infallible. There are only systems that have been compromised or will be compromised. As stated earlier, we are willingly taking some level of vulnerabilities, and from time to time, these vulnerabilities might be used against us. So it's always important to prepare our incident response plan and always prepare to handle the worst. Here are some of the references we used for this discussion. Thank you for listening.